This is your worksheet for descriptive geometry today. This is the second half of descriptive geometry. But on this first page here, it's just applying information that we learned last week. And the goal for this first page is finding the angle between planes A, B, E, and BCE here. And this is, if I want to draw it, it's like in a side view, kind of like this. It's just a pyramid that we're looking at, and we're looking down the top here in the top view and the side in the front view, or we're looking at the front in the front view. Now, let me just write our goal here. Goal, obtain an edge view of both planes to measure angle. So if we imagine these two planes are like my two triangles, then if we're looking straight down on the edge of the triangles in an edge view of both of them, then we'll be able to see the angle between the two planes. And in order to do that, so for our first step, we need a true length line that lies on both planes. And what line lies on both planes? Well, that is line EB, because that's the intersection of the two planes. So if we find this line EB in true length, we can then, as our second step, find point view of the true length line. This will result in an edge view of both planes. And then our third step is just to measure the angle. So let's start with the first thing. So we have EB here. This is the line that is the intersection between this plane and this plane that we want to see the angle. And we can first check, do we have it in true length already in either of these views? And we can check that by seeing if it is parallel to the fold line in either view. And we can see EB here is not parallel to this fold line, and EB here is not parallel here. So the first step, we're going to have to add a parallel fold line to EB and then project points across so that we get EB in true length. And then we can find the point view of EB. So I'm going to take my triangles here and go parallel to EB and add a fold line like so. And now I'm going to project all of these points perpendicular to that fold line. So I have BC here, E here, and AD here. And now remember, we're making a view here, and in order to find where these points are on these projection lines, we need to measure two views back. So I'm not measuring from this view. This is view 1. This is view 2. So B is going to be about this distance from the fold line. Oops. Here, and you guys can use your dividers instead of your compass, but I kind of like to use the compass. So that's B. C is going to be this distance here, and remember, you're always measuring from the fold line, not from the edge of the part. I'll erase this 3 here. I don't need to extend that projection line. D is going to be the same distance as C, as you can see, so I can reuse that same measurement. And then A is going to be the same as B, which is here. And technically, I don't need to project point D. Oh, sorry, this A is over here. Technically, I don't really need point D, but I'm going to project it anyways so that we can see the whole part. E is actually this distance, and I'm going to add a projection line here. And this is what I've been telling you guys, is to add projection lines for your measurements so that you know you're measuring the true distance and not measuring at some angle and measuring a longer distance. So E is actually here, and I'm going to erase this point here. So I'm going to label these. This is E, and this view is looking this way. So I'm going to see A here and D here, because A is the closer number, or the closer letter, and B is also the closer letter. And then I need to extend this projection line here, and this is C. And now I can connect these. I know that A and E are connected, and E and D are connected, and I know that B and E are connected, and E and C are connected, and then these are the bottom edges of this pyramid. And so now I'm looking at my pyramid on the side, and this is EB, which is true length now, because we went over a fold line and it was parallel in this view, meaning the resultant view makes it true length. Another thing you can see here is EC. This is also EC here, and the EC is also parallel to this fold line, meaning that this line is also going to be true length. And also BC, if you remember your 4 rules of descriptive geometry that we went over last week, if a line going across a fold line becomes a point, so this BC here is becoming a point after I go over this fold line, then it is true length here as well. So that makes this line true length as well. And if all of these lines are true length, then this plane is true size and shape here. But we're not looking for true size and shape. We're looking for the angle between ABE and BCE. So the second step here is to find BE as a point view, and to do that we need to go make a fold line perpendicular to this true length line. and now I have a fold line perpendicular to that, and we are again going to project all of these points beyond this fold line. And I'm just going to do all of them so we have the entire part. And you can see E and B share the same projection line. Now I have all these projection lines. Now to find where the points lie on these projection lines, I go back to views again. So I'm going back 1, 2, so over this fold line, over the second fold line, and now I'm measuring these distances for where my points are. So now I'm going to measure BC, and I made my fold line very close. So B and C are going to be this distance, as well as E. All three of these points are going to be the same distance from this fold line, and A and D are going to be this far. So A is here, D is here, and I forgot to get C earlier, and C is here. And D is the same as A. Yes, okay, so now I have D here, C here, E and B here, and we're looking this way, so B comes first because I see B first in this view and then E. So I have B comma E, and then I have A here. Now I'm going to connect all these points. So this line is connected, and these 2 points are connected. And you can also see that C and D are connected, but before I connect those, I'm going to explain what's going on here. So this A, B, E here is this plane, A, B, E, and we see it as a line because we have it as an edge view. Now we also see B, E, C here, B, E, C, as an edge view here. So this angle here, theta, is the angle that we're looking for. But we also have the rest of the part here. We're looking at the bottom of this part, so we're kind of looking underneath this part. And since we're looking at it at an angle, it's displayed as somewhat of a parallelogram. And I'm just going to complete that. So we have a line here, and A and D are connected as well. And because this is the bottom view, D and E are connected, but it's going to be a hidden line since we're looking from the bottom. But now we have an edge view of these 2 planes, and we can calculate, or we can measure the angle. So if I continue these lines out and project them out, I can use my protractor to measure. And I have my protractor here. The way you can use this is there's a tiny little mark in the middle. Just line that up with the angle, or with the center of the 2 lines, and then rotate it so that one edge lands on 0 where you drew your projection line. And then if you follow this outer number across on your compass, you'll see 10, 20, 30, 90, and it lands right on 99 degrees here. So I get that theta is 99 degrees. And that's my angle between these 2 planes. Now let's go on to the next page. And this is a new topic, which is showing the visibility of the 2 lines, And you may be wondering, what does that mean? Well, in this case, we're given two lines that are in three-dimensional space, angled in all three dimensions, and we have two views. And because we have two views, we have enough information to discover what angle these lines are in space and to determine which line is in front of the other or on top of the other in the top view or the front view. But the first thing is we want to determine, do these lines actually intersect? And the easiest way to do that is to add a point at the apparent intersection where we think there may be an intersection and project that point vertically into the other view and determine if it lines up with the apparent intersection in the other view. And we can see here that it does not. And if they did intersect, this point would be the same point in this view, and they would line up in both views. Now, because they don't line up, that means that this point does not lie on both lines, and therefore these lines do not intersect. But if these lines were collinear, we would know that these two lines are intersecting lines, but because they're not, we know that these are called skew lines. They do not intersect. So I can project both of these points down, and I'll just write our goal here. Which line is on top or in front? And you might be wondering, these are like pipes here and not lines. Why are they drawn like that? It's just because it makes it easier for the assignment to show that you know which one is in front. So just imagine that these are two just very wide lines or two pipes in 3D space, and we can dash the edges or make the edges solid to show which one is on top and which one is on the bottom. So in order to do this, we've already determined, do they intersect? And we said no. Do they intersect? No. So our first step then is to label and project all points. And to do this, I can just label the points, and these are just the endpoints of the line. I'm going to label this A, B, and C, D. And you might wonder, how do I know which of these endpoints are A, B, C, or D? Well, you know when projecting across a fold line, the width dimension between the front and the top view are conserved, meaning that a point here has to lie along a vertical projection line between the two views. That means that the only option I have for A is this point here. A cannot be here because it doesn't line up horizontally with this point. So because I know where they are, I'm not going to line up my triangle with the fold line, but I'm just going to project them down. And I can see here it is a little tricky. So I am going to use my triangle to figure out which of these points is which. And if I project B down, I can see B is here. And if I project D down, I can see that D lines up with this guy. So this is B, and this is A, and we can see that BA and BA are here. If I somehow got that this is D, then we would have a line that doesn't exist. There is no DA in these two views, and so that makes this C, and that makes this D. And then I can label the apparent intersections as 1 and 2 here. And now we have all the points labeled, so step 2 is going to be project the apparent intersection and then find which point, which line that projection line meets first, and that will tell us which line is on top. So for example, I've projected this apparent intersection in the front view, and projecting that line up, this line meets CD first, and you can just remember that as a rule. That means in this view that I projected this point from, CD is on top. So to show that, I can make this a solid line here and a solid line here. And that means the other pipe here is on the bottom. So I can put dashed lines or hidden lines in that view. So you can see CD is on top and AB is behind it. Now I can do the same thing with this view. If I follow this projection line from the apparent intersection down, it meets AB first. So that means AB is on top, and I can add solid lines here. And that means CD is on the bottom. And I can add hidden lines here. So that's how to find the visibility of two lines. When we say visibility, we just mean which one is in front and which one is behind. Now, the second part of this paper, or this second example, just has several lines, and you'll have to project the apparent intersections multiple times from both views to the above and below, and you'll also have to project each of these endpoints to find out which endpoint is which. For example, I know that this point here is H, and if I project point I here down, it is the farthest one out, and that means this is point I. And then I can do the same thing with another intersecting line. Let's say this is point D here. I can project this point and find that this line is D, and then follow C and find that this is C here. And then I have CD, CD, HI, HI, and I can project their apparent intersection, which is this point and this point here, and find if they line up or not. And they're pretty close, but not quite. So I can see here that CD coming down, the first line that I meet is CD here, which means that in this view, CD is on top. So I'll add a solid line here and hidden line here. And if I follow this projection line up, I meet HI first, which means that HI is on top in this view. And CD, forgot to label this point, CD is on the bottom in this view. And you guys can do that for the rest of these lines here on your own. Now, the last part of this worksheet is determining the pierce point of this line with this plane. So again, this is just a random plane oriented in 3D space, and we have a top view and a front view of it, and a random line oriented in 3D space that we are told intersects this plane. If you were to extend a line that is not parallel to a plane infinitely and extend the plane infinitely, we'll always have an intersection, but we are told within the bounds of this plane we have an intersection. So to determine where the pierce point is between this line and this plane, we actually have two methods that are outlined in the book, but the method that we are going to use is called the cutting plane method. And there's a lot there. It's a little complicated why it's called the cutting plane, but just remember these steps here. Our goal, again, is find the pierce point. And visibility. So the first step is to label again and project apparent intersections. So here I can call this where the line intersects here with the edges of this plane. They don't actually intersect, but that's why we call them apparent intersections. They somewhat look like they intersect, and I can label this Y and this point X and project them down. And when I project them down, I am finding where this point on edge AC is in the bottom view. So I see that this is edge BC, but I'm trying to find where this point is on AC. So I'm going to project this down, and I find that it is here. So this is Y. So this is why I skipped this line BC, because this point Y is on AC. So I brought it down onto AC here. I'm going to do the same thing with X. And X is on BA. So I come down to BA here, and I have my point X here, and I'm going to connect these 2 points in a line in this view. With just a light projection line, and then I'm going to connect the line, the true line, with the projection line in this view as well. And then where this line between these 2 edge points of the plane intersects the line that is intersecting the plane is your pierce point. And I'll just call this point P. And to find where the pierce point is in this view, we know that any point in one view also, again, is the same horizontal distance in your coordinate system in the adjacent view. So we can just bring that point up with a projection line. And because we know P is on this projection line somewhere in this view, and is also on XY here. I guess I used XY twice. Let me change these to 1, 2, 1, 1, 2, and 2. This point here is going to be P as well. So this is our pierce point in this view. Now we need to find if our line XY is in front of the plane in this side and behind on this side, or vice versa, and then the same thing in this top view here. And the way we can do that is just follow the same steps that we followed for line visibility of lines, and just treat this line and the edge of a plane as two lines that have an apparent intersection that we are trying to discover their visibility. So step 2 is determine visibility of edge of plane and piercing line. And we can do this twice. So I can pick either side, and I know the opposite side of the pierce point is going to be the opposite of the side that I'm determining. So for example, I can determine if AC is on top or behind XY by projecting this apparent intersection to the top view and determining which line that we meet first. And I can see of the two lines XY or AC, I am meeting XY first, and that means that in this view XY is on top of AC or in front of AC. And since the line is piercing this plane, I know that on this side of the pierce point, the line is behind the plane. So I can put hidden lines here. So the line is starting out in front of the plane, piercing it, and then ending up behind the plane. Now I can do the same thing for this view. I can take the apparent intersection of the line XY and AB and bring a projection line down and see which line it meets first. And I can see that this projection line meets XY before it meets AB here, and that means that XY is on top on this side in this view, so the opposite side of this view. And so my line is on top of the plane on this side of the pierce point and behind the plane on this side of the pierce point. And that's how I determine or discover the visibility and pierce point between a plane and a line oriented in 3D space. So again, first we're finding where that pierce point is by projecting the apparent intersections down and creating a line that comes across. And the reason this is called the cutting plane method is because this line here represents another plane that is intersecting this plane and creating a line that comes across. And where that line coming across meets our original line is the pierce point. And then after we find that pierce point, we can find which side the line is in front and behind the plane by projecting the apparent intersections and treating the edges of the plane and the line as two lines whose visibility we are trying to determine, just like we did with these lines here.